Welcome to the Deep Dive. Today we're diving into the world of programming for data science.
Sounds exciting.
It is. And to guide our deep dive, we have this roadmap from Data. Think of it as our coding syllabus, but before we even sign up for class, it breaks down the skills and tools you need and even estimates how long each step might take.
Ambitious.
It is, right?
Yeah.
What jumps out at you from this roadmap?
Well, first off, this isn't a weekend workshop, you know?
Right.
This roadmap suggests a solid 12 to 20 months commitment, and that's it if you're putting in serious time, like 3 to 5 hours a day.
Wow, yeah.
It's a marathon, not a sprint, that's for sure.
Totally. And like any good marathon, you need the right gear.
Absolutely.
And this roadmap is basically screaming that Python is those essential running shoes for data science. Why is Python the language for data science?
Well, Python's popular for a reason, especially in data science. It's relatively easy to pick up, which is great for beginners, but it's also seriously powerful. And the real game changer is its libraries. Think of them like specialized toolkits built right in. So you've got NumPy, for example, that can crunch huge data sets ridiculously fast.
Like a super-powered calculator almost.
Exactly. Then there's Pandas, which is like your data wrangling superhero. Imagine cleaning up messy spreadsheets with thousands of entries, but you do it in a few lines of code. Pandas makes that happen.
That's pretty handy.
Oh, absolutely. And then when you're ready to present your findings, there's Matplotlib.
Okay.
It helps you create stunning visuals, to tell the data's story in a way that everyone can understand.
Okay, so Python is the star, clearly. But even a star needs a good support crew, right?
For sure.
And the roadmap mentions version control with Git from the get-go, even for beginners. Why is that so vital right from day one?
It's all about collaboration and preventing coding nightmares down the line. Picture this. You're working on a complex project, making tons of changes.
Right.
Then you realize you took a wrong turn way back. Git's like a time machine. You can track your progress, go back to earlier versions if things go south, and work seamlessly with others without messing up each other's code. It's a lifesaver, especially when you're just starting out.
Okay, got it. Get our coding time machine. But moving on, the roadmap dives deep into data structures and algorithms, like a whole college course packed into this journey. Why is this crucial for data scientists? Isn't that more for, like, software engineers?
It's a common misconception that data scientists can skip those hardcore computer science concepts, but understanding data structures and algorithms is like having the blueprint for efficient problem solving. It's like building a house. You could do it without a blueprint, sure,
Right.
but it might end up lopsided and inefficient. Knowing how to organize data efficiently, that's your data structures, and understanding the steps needed to solve problems, your algorithms, is how you write code that runs smoothly, especially with giant data sets. We're talking the difference between a program that takes hours versus minutes to run.
So it's about making sure our data science house doesn't crumble under the weight of big data.
Exactly. And it's not just speed, it's about picking the best solution for a problem. It's about clean, scalable code that can grow with your projects.
So we've got our Python foundation, our Git time machine, and our blueprint for efficient problem solving with data structures and algorithms. What's next on this adventure?
Well, every adventurer needs to know how to communicate, and in data science, that language is SQL.
SQL, the language of databases. But why is it so vital in the data science toolkit? I always thought that was more for database administrators.
You'd be surprised how much time data scientists spend wrestling with data. And a lot of that data lives in databases. SQL is how we talk to those databases, how we ask questions and get answers. It's like trying to find a specific grain of sand on a beach. SQL is your metal detector, helping you sift through it all and pull out exactly what you need.
So it's less about being a database guru and more about getting the specific data W you need for analysis.
Exactly. It's mastering the art of the query,
Yeah.
You can extract specific data points, join information from different tables, filter and sort results, even do calculations right within the database. It's fundamental.
Okay, Python, Git, data structures and algorithms, and SQL. We're building quite the data science arsenal here. But I'm guessing the roadmap doesn't stop there.
Oh, there's more, for sure. Now we're getting into the bedrock of data science. Math and statistics.
I can already hear some listeners hitting the skip button. But seriously, why are these foundational subjects so crucial for aspiring data scientists?
I get it, math and stats can be intimidating, especially if it's been a while. But think of it like this. You wouldn't build a bridge without understanding physics, right? Math and statistics are the physics of data science. They give you the tools to understand how data behaves, how algorithms learn from it, and how to interpret your results.
So less about memorizing formulas and more about understanding the principles behind how data works.
Exactly. Like linear algebra helps you grasp how algorithms process data at a core level. Calculus is essential for optimization, which is basically finding the best solution. And that's huge in machine learning.
Good.
Then you've got probability and statistics, which are all about understanding data distributions, testing hypotheses, and building models that can make accurate predictions.
Right. So we've covered a lot. Python for coding, Git for collaboration, data structures and algorithms for efficiency, SQL for wrangling databases, and the sometimes dreaded but crucial math and statistics for understanding the data itself. It's like we're assembling a data science superhero, one skill at a time.
It is a lot, but Rome wasn't built in a day. It's about building a solid foundation brick by brick. And trust me, things are about to get even more exciting as we move forward.
Well, now I can't wait. What's next on this data science syllabus of ours?
Well, now that we have our toolkit, it's time to make data come alive with data collection and visualization. This is where things start to get really visually appealing.
Yeah, data collection and visualization. This is where we take that raw data, clean it up, transform it into something that actually makes sense. It's like taking a diamond in the rough and polishing it until it shines.
Okay, I like that analogy. And the roadmap specifically calls out data cleaning as a crucial first step. Why is that so important? I mean, isn't all data, ready to be analyzed right away?
I wish it were that easy. Real-world data is messy. Think of it like a teenager's room, full of potential but completely disorganized.
Okay, I can see that.
You've got missing values, errors, duplicates, maybe some outliers, data points that are way off from the rest.
Right.
Cleaning all that up ensures that you're working with reliable data before you even think about analysis.
So it's about making sure our data is, I guess, trustworthy, right? Before we jump to conclusions,
Exactly.
what kind of techniques are involved in that data cleaning process? Well, there are a ton of techniques. The roadmap highlights some key ones, like filling in those missing values, using statistical methods, or removing duplicates to avoid bias. Dealing with outliers often requires a bit more thought, Sometimes they're genuine anomalies, other times they're just errors that need fixing.
Right, so it's a mix of technical know-how and good judgment.
Absolutely. Then comes data transformation, which is getting your data into the right shape and format for analysis. This might involve techniques like normalization, where you rescale the data to a standard range, or standardization, where you adjust it to have a mean of 0 and a standard deviation of 1.
Okay, so it's like tailoring the data to fit what we need.
Exactly. And often you'll be working with categorical variables, which are non-numerical data, like colors or categories.
Right.
You need to encode these into a numerical form that algorithms can understand. So you might assign a number to each color, for example, or create dummy variables to represent different categories.
So we're teaching our data to speak computer language.
In a way, yeah. And once the data is clean and transformed, the fun part begins, exploratory data analysis, or EDA for short.
Okay.
This is where we really dig into the data, looking for patterns, trends, relationships, the good stuff.
Okay, so this is where things get interesting.
This is where the magic happens. EDA involves using summary statistics like calculating the mean, median, standard deviation, but it's also about visualizing the data, seeing the patterns emerge visually.
So charts and graphs and all that.
Exactly. The roadmap stresses the importance of creating those visuals to reveal trends that you might miss just by staring at numbers in a spreadsheet.
So data visualization is like giving our data a voice, letting it tell its story visually so we humans can grasp it.
Perfectly put. And there's some amazing tools for this, like Matplotlib.
Yep.
It's a Python library that gives you a lot of control over how your graphs look. Then there's Seaborn, which builds on Matplotlib and offers a more streamlined interface with pre-built themes and color palettes, making it easy to create stunning visualizations with just a few lines of code.
It's like picking the right brush for your painting then.
Exactly. And the type of visualization you choose depends on your data and the questions you're asking. You might use scatter plots to explore relationships between two variables, histograms to understand data distribution, bar charts for comparing categories, or line charts to show trends over time. The key is choosing the visualization that best tells the story hidden within the data.
It's not just about making things look pretty then. It's about the right visual for the job.
Right, exactly.
Now, what about when our data comes from multiple sources? How do we combine it all?
That's data integration, a key part of real-world data science. You might be pulling data from databases, spreadsheets, even web APIs. It's like piecing together a puzzle, making sure all the pieces fit.
Okay, I see.
Right.
So data collection and visualization are more than just cleaning and processing then. It's about turning raw data into a story we can understand.
Exactly. And that brings us to the next exciting stage, machine learning. This is where we empower computers to learn from data and make predictions.
Now we're talking. Machine learning, that's where things get really futuristic. What can you tell us about this mysterious realm?
Well, it's like teaching a computer to recognize patterns. We feed it tons of data, and it learns to identify relationships that would be nearly impossible for humans to spot.
Hmm.
Then, it uses this knowledge to make predictions on new data it hasn't seen before.
So it's like training a digital detective to solve crimes based on past cases.
That's a great way to put it. The roadmap breaks machine learning down into two main types, supervised and unsupervised learning. With supervised learning, we give the algorithm labeled data, meaning we already know the outcome, like giving our detective the case file with all the clues and the solution.
Right.
The algorithm learns from this labeled data and builds a model that can predict the outcome for new cases.
What kind of problems can we tackle with supervised learning?
Oh, a huge range. If we want to predict a continuous value, like the price of a house or tomorrow's temperature, we use regression algorithms. The roadmap points to linear regression as a classic example. If we're predicting categories, like whether an email is spam or if a customer will click on an ad, we use classification algorithms.
Got it.
Things like decision trees and k-nearest neighbors are popular examples there.
Okay, so supervised learning is about making those predictions based on labeled data. What about unsupervised learning? How's that different?
With unsupervised learning, we don't give the algorithm the answers up front. It's like giving our detective a bunch of evidence without telling them what the crime is.
So they have to figure it out themselves.
Exactly. The algorithm has to figure out the underlying structure of the data all on its own.
So it's more about exploration and discovery, letting the data reveal its secrets.
Exactly. One common task is clustering, where the algorithm groups similar data points together based on their characteristics. Imagine trying to segment customers into different groups based on their buying habits. That's a classic clustering problem. The roadmap mentions k-means and hierarchical clustering as common algorithms here.
Okay, interesting.
Another important task is dimensionality reduction. This is where we reduce the number of variables in our data while still keeping the essential information.
Okay.
This can help simplify things and boost the performance of machine learning models down the line. Principal component analysis, or PCA, is a popular technique for this.
So it sounds like unsupervised learning is more open-ended and exploratory, while supervised learning is focused on specific predictions.
That's a good way to think about it. But how do we know if our machine learning models are any good?
Yeah, that's a good question. It's like we need to grade our digital students somehow. How do we actually measure how well they're performing?
That's where model evaluation comes in. And it's a crucial step that often gets overlooked.
Right, model evaluation. It is like grading our digital student. But how do we measure the performance of these machine learning models?
It all comes down to picking the right metrics for the task. For classification problems, accuracy is a common one. It tells you what percentage of predictions the model got right. But accuracy alone can be misleading, especially if you have imbalanced data. That's why we often look at other metrics like precision, which tells us how many of the positive predictions were actually correct, and recall, which tells us how many of the actual positive cases the model caught.
So it's not just about getting it right, but also about avoiding false positives and false negatives.
Exactly. And the F1 score combines precision and recall into a single metric, giving us a more balanced view of the model's performance.
So it's like a report card with multiple grades, giving us a better overall picture of how the model's doing.
Yeah, that's a good analogy.
Are there other tools we can use for evaluation?
Absolutely. The confusion matrix is great for visualizing the model's performance. It shows you how many predictions were right and wrong for each category so you can clearly see where the model's making mistakes. Really helpful for understanding its strengths and weaknesses.
So it helps us pinpoint areas for improvement.
Exactly.
Now, what happens after we've evaluated our model? We've given it a grade. Now what?
Well, building the model is just the first step. The roadmap emphasizes model training, which is all about fine-tuning the model to improve its performance. This involves techniques like train test splitting, where you divide your data to train the model and then test it on unseen data.
Okay, so it's like practice exams.
Yeah, exactly. And cross-validation takes that a step further, splitting the data multiple times for a more robust evaluation.
Okay.
And then there's hyperparameter tuning.
Hyperparameter what?
Hyperparameter tuning. Think of it like adjusting the settings on a machine to get the best performance.
Got it. Fine-tuning.
Yeah.
Now, even with all this training, are there still challenges we need to be aware of? The roadmap mentions something called overfitting and underfitting. What are those, and why should we care?
Overfitting is when a model basically memorizes the training data but doesn't understand the underlying patterns. It's like a student who aces a test by memorizing the answers but can't actually apply the concepts. Underfitting, on the other hand, is when the model is too simple to capture the patterns in the data, like a student who didn't study enough and just blanks on the test.
So we need to find that sweet spot.
Right. We need a model that's complex enough to learn, but not so complex that it just memorizes the training data and fails when it sees new data.
Makes sense. Now, how do we avoid those pitfalls, like overfitting?
There are techniques for that. Regularization adds a penalty for complexity, preventing the model from getting too carried away with memorization.
Okay.
And dropout randomly drops out some connections in a neural network during training. This helps the model focus on the most important features and not get bogged down in irrelevant details.
So it's all about making sure the model generalizes well to new data.
Precisely.
Wow, we've covered a lot with machine learning. From those two types of learning to model evaluation and the challenges of overfitting and underfitting, it's clearly a deep and complex field.
It is, definitely.
But the roadmap doesn't stop there. It throws in something called deep learning, which sounds even more intense. What's the story with deep learning, and why is everyone talking about it in data science these days?
Deep learning is like machine learning on steroids. It uses these artificial neural networks with many layers, that's where the deep comes from, to process information in a way that's inspired by the human brain. These networks can learn very complex patterns from massive amounts of data, leading to some incredible results in many areas.
So it's next-level machine learning, building even more sophisticated models to handle even more complex problems.
Yeah, you could say that.
What are some real-world examples where deep learning is making an impact?
Deep learning is transforming a lot of fields. Convolutional neural networks, CNNs for short, are used for image recognition, allowing computers to identify objects, faces, even emotions in images.
Wow.
And recurrent neural networks, or RNNs, are designed to handle sequential data, making them perfect for natural language processing, speech recognition, machine translation.
It sounds like deep learning is powering a lot of those futuristic technologies we hear about, like self-driving cars and virtual assistants.
Absolutely, it is. And the roadmap covers some of the key concepts, including activation functions, which determine how neurons fire, forward propagation, which is how information flows through the network, and back propagation, the process of fine-tuning those connections.
Wow, that's a lot of complicated stuff.
It is, but it's also incredibly fascinating.
It is. The roadmap also mentions popular deep learning frameworks, like TensorFlow and PyTorch.
Yes, these provide the tools and infrastructure to actually build and train those complex models.
So with all this power, is deep learning something every aspiring data scientist needs to master?
Well, while deep learning is super powerful, it's not a one-size-fits-all solution. The roadmap emphasizes specialization. It suggests choosing a specific area of data science to focus on and becoming an expert in that niche.
So finding your specialty within the vast data science world.
Exactly.
What are some of the popular specializations the roadmap mentions?
Two big ones are natural language processing, or NLP, and computer vision. NLP focuses on teaching computers to understand human language, which has led to things like chatbots, sentiment analysis, and machine translation.
Okay.
Computer vision is about teaching computers to see and interpret images and videos, opening up possibilities in object recognition, image classification, even medical diagnosis.
Both sound incredibly exciting and challenging. What kind of skills would you need to specialize in those areas?
For NLP, the roadmap mentions techniques like tokenization, breaking text down into individual words or units, stemming, reducing words to their root form, and lemmatization, which converts words to their base form.
So it's all about preparing the text for the computer to analyze.
Right. It also highlights tasks like sentiment analysis, figuring out the emotional tone of a text, and named entity recognition, or NER, which is about identifying entities like people, places, and organizations.
NLP really is about bridging the gap between human language and computers.
Is.
Now, what about computer vision? What are some of the key skills there?
Computer vision involves tasks like image classification, where you train models to categorize images, object detection, finding and locating specific objects within an image, and image segmentation, dividing an image into meaningful regions. It also mentions generative adversarial networks, or GANs, which are capable of generating incredibly realistic images and videos.
So it's pushing the boundaries of what computers can do with images.
Definitely.
But the roadmap goes even further, mentioning big data. Why is that relevant to data science, And is it a must-have skill for every aspiring data scientist?
Big data is all about dealing with massive data sets that are just too big for traditional methods to handle. These data sets are common in industries like tech, finance, and healthcare, where a huge amount of data is generated every day.
It's about handling the data deluge then.
It is, and the roadmap highlights big data frameworks like Hadoop and Spark, designed to process and analyze this data across multiple computers. It also mentions data processing techniques like MapReduce, data storage systems like HDFS and NoSQL databases, and data ingestion tools like Kafka and Flume.
Wow, so big data is a specialty within data science, requiring its own set of tools and expertise.
That's right. While it's not essential for all data science roles, having those big data skills can really set you apart, especially if you're interested in working with massive data sets and tackling those really challenging problems in industries that rely heavily on data.
This roadmap has taken us on quite a journey. We've covered everything from the basics of programming to the complexities of deep learning and big data. It's clear that becoming a data scientist requires a diverse skill set, a passion for learning, and a lot of dedication. What are your final thoughts on this roadmap? And what advice would you give to someone just starting their own data science adventure?
This roadmap is a great starting point for anyone entering the world of data science. It lays out the essential skills and tools needed to succeed, providing a clear path forward for those willing to put in the work. But remember, it's just a guide. The real adventure starts when you begin exploring, experimenting, and pushing the boundaries of what's possible with data.
So it's not just about ticking boxes and mastering those technical skills. It's about embracing the journey, staying curious, and always learning.
Exactly.
What excites you most about data science?
I'd say it's the potential of data science to make a real difference in the world. From healthcare to finance, from environmental science to social good, data science is being used to tackle some of the biggest challenges facing humanity. And it's a field that's constantly changing, with new discoveries and applications popping up all the time.
That's inspiring. What advice would you give to someone who's just starting on this data science journey?
Don't be afraid to jump in and get your hands dirty. Play around with different tools, try real-world projects, and connect with other data scientists. Learn from their experiences. The journey might feel overwhelming at first, but it's also incredibly rewarding.
That's a great point to end on. Thanks for joining us for this deep dive into the world of programming for data science. It's been an amazing exploration, and I hope our listeners feel inspired to start their own data science adventures.
Keep learning, keep exploring, and most importantly, have fun.
And until next time, on The Deep Dive, keep diving deep.